Hi everyone, and welcome to the second side event of day 3 at the top at IPCC event side event place. The session focuses on early warning signs of sea level rise from the world's largest ice sheet in West East Antarctica. And we have 3 experts who are supposed to speak today, but unfortunately Matt King lost his connection flight, so he won't be here. But we have Chris Stokes and Facility McCormick online today. So yeah, I'm very happy to introduce our first speaker, Professor Chris Stokes, based in Durham University. He's a world expert in observing mountain glaciers, both using remote sensing and fieldwork. So I'm really happy to welcome Chris and for you.
Thank you. Yes, so this is another update really of what's happening to the East Antarctic Ice Sheet, which is actually the world's largest ice sheet. And it's an ice sheet that for a long time we thought was relatively immune to climate change. I remember digging out a paper a few weeks ago from the 1990s saying that it would take 17 degrees of warming before we saw this ice sheet react. And gradually over the last 2 or 3 decades, that figure's come down. And I think it's fairly clear now that somewhere between 1.5 and 2 degrees, we would expect to see a response to this ice sheet. So for those who don't know, ice sheets contain around 65 meters of sea level equivalent. 7 and a bit meters of that is in the Greenland ice sheet, and the rest is in Antarctica, which obviously stores the vast majority of Earth's ice. And the East Antarctic Ice Sheet is by far the world's largest ice sheet, an order of magnitude larger than the West Antarctic Ice Sheet. And you can see it here on the map, outlined in red. And it's very interesting. You can just scan the literature. It's actually attracted much less attention. I've just kind of done a bar chart here from the 1950s through to present of the number of papers on either the East Antarctic Ice Sheet or West Antarctic Ice Sheet. And the West Antarctic Ice Sheet's in black. And you can see there that it's dominated the literature. And that's because we've observed some really worrying signs of mass loss in West Antarctica. We know it's contributing to sea level rise. But perhaps because there's a kind of sense that East Antarctica is more stable and less vulnerable to climate change, there's been less literature. East Antarctica is also more difficult to get to. There's been less field work there. And there's still lots of glaciers there that we know very little about. So there are much larger uncertainties. But certainly in the last few years, people have started to look at East Antarctica in a bit more detail. And the bottom plot here is showing you the sea level contribution from the different ice sheets. And you can see Greenland in blue, which seems to be clearly contributing the most. The Antarctic contribution is in purple, and that's dominated by West Antarctica. And at East Antarctica, the mass balance of East Antarctica is that broad orange line that runs along the top. That broadly seems to be in balance. There are some studies showing that it might be losing mass slightly, and some should say it might be gaining mass slightly, but overall it seems to be in balance. So whilst the combined contribution of ice sheets is now 4 times higher than the 1990s, and there's a sense that that's accelerating, and Greenland and West Antarctica contributed over 20 millimeters of mean sea level, the IPCC concluded that it's currently unclear whether mass loss of the East Antarctic ice sheet over the last 3 decades has been significant, as much suggested, such as the paper by Riga tell that, or essentially it's zero with very large uncertainties. And this is something that we've been looking at, that several people, groups around the world have been looking at. So in today's slide event, I was just going to introduce what's happened to East Antarctica during the past warm periods. I think we sometimes forget with only 20 years of observation data and large uncertainties that we do have quite a valuable record in the past. And so I'll be looking at particular periods, 4 or 5 particular periods in the past where temperatures were either as warm or even just slightly warmer than present, and see what East Antarctica did. And then Matt King was supposed to be here to talk about kind of current observations and some of the surprising things we've seen over the last few years, particularly actually in the last year. And unfortunately, he's not here, so I'll be taking you through his slides. And then we've got Felicity McCormick, who's an American ice sheet modeler, who's been doing lots of work on East Antarctica, and she'll be taking you through some kind of future projections online, and then I'll just wrap up briefly with a concluding slide at the end. So one of the things that I think we have to be aware of is that an ice sheet is vulnerable to instability or to rapid retreat. when it rests on a bed that's well below sea level. This is known as a marine-based sector or marine-based ice sheet. And West Antarctica, most of West Antarctica is marine-based, and some of its mass loss we think is connected to the fact that there are emerging signs of instability. Actually, East Antarctica also has three major marine-based sectors, each have the order of about 3 to 4 meters of sea level equivalent. So it's almost like we have three mini West Antarctic ice sheets within East Antarctica. And paleo sea level records, ocean sediment records, ice sheet modelling of the past all indicate that they were particularly vulnerable to past war periods. So I've just put the stars on the slide there where they are. We have the Wilkes subglacial basin, we have the Aurora subglacial basin and the Recovery subglacial basin. And these kind of blue areas on this map which are showing you the bed elevation. These are parts of the ice sheet that are currently resting on land that's well below sea level. And sometimes, 1 to 2 kilometers below sea level. So the first warm period I wanted to take you to was the mid-Miocene. Now, this is in the deep past in many ways, 17, 14 million years ago. We know global atmospheric temperatures were 7 to 8 degrees warmer. There was a very strong what we call orbital forcing. The Earth was receiving some stronger insolation in summer. But interestingly, model studies have shown that when you force the Antarctic ice sheet with CO2 concentrations for around 280 to 500 parts per million, then actually not only do you deglaciate West Antarctica, but you also deglaciate all three of the marine basins of East Antarctica. And we know from some of these modelling experiments that it could have contributed tens of meters of sea level equivalents. Okay? With CO2 concentrations similar to those which are projected over the next century or so. So we're currently at about 420, 424 parts per million, and we can force a model at that time, and we clearly deglaciate parts of East Antarctica. A little bit further into the I guess close to us in time, the mid-Pliocene. This is perhaps a bit more analogous to some of the projections where we might be heading over the next century, 2 centuries maybe. Atmospheric temperatures 2 to 4 degrees warmer than present. That's certainly consistent with what kind of current pledges, where current pledges will take us in terms of temperatures and CO2 concentrations. In fact, CO2 concentrations during the mid-Pliocene were actually around about the same levels today. But we know that global mean sea level was 10 to 25 meters higher. What that tells you is that you probably lost Greenland, you probably lost parts of West Antarctica, and certainly at the higher end there, you must have also deglaciated parts of East Antarctica. And again, some modelling that's been done shows that the Wilkes subglacial basin, the Aurora, and the Recovery, all three basins retreating just at the kind of same time that we see West Antarctica collapse as well. So modelling suggests a multi-meter contribution from East Antarctica during the mid-Pliocene. We'll come a bit closer, an interglacial that again is not dissimilar from the interglacial that we're currently in, what's called marine isotope stage 11. This is a warm period about 400,000 years ago. Atmospheric temperatures again 1 to 2 degrees warmer than present. Sea level not quite so high as the mid-Pliocene, maybe 6 to 13 meters. And there's been some studies that show quite clearly that parts of the Wilkes glacial basin, you see it here, a whole chunk was taken out of that, maybe 700 kilometers of retreat, potentially adding 3 to 4 meters to global mean sea level. So it's a kind of mini West Antarctic response from East Antarctica during stage 11. There was another warm interglacial, stage 9, not quite so warm, but maybe we saw almost a meter, 90 centimeters of sea level right there. There's actually a growing body of evidence. Most of these papers actually are since the last IPCC report, and so there's a growing body of evidence emerging of East Antarctic ice sheet instability in the paleo record. And then a very kind of common or useful target as well is actually the last interglacial, which is known as marine isotope stage 5, around about 125 to 122,000 years ago. Quite accurate measurements of paleo sea level, maybe 6 to 9 meters higher, is generally being assumed that East Antarctica didn't lose any mass, but that higher sea level was mostly from Greenland and West Antarctica. And again, there's a number of studies that have come out in the last few months suggesting that maybe there are parts of East Antarctica, particularly in the Aurora subglacial basin over here, possibly the duration, and we're not always sure exactly how long we need to keep the temperatures elevated to see that response. But I think what's going to unfold in the next part of this session, under part two, is that actually we are seeing signs of a dynamic instability emerging in parts of East Antarctica that would be consistent with the early signs of response from this ice sheet. So this is where Matt King would hopefully have been stood here, but he's en route from Singapore at the moment. Unfortunately, his flight connection was missed. I've got his slides, and I'll be taking you through them. He can hopefully do a reasonable job. But the title of this part of the talk: Changes and Surprises Emerging from East Antarctica. And I think that is a really good title, particularly in terms of the last 6 to 12 months. Because in the last year, we all know 2023 has been one of the going to be the warmest year on record. And actually, it's been affecting East Antarctica. There's some strange things been happening, and I'll go through those now. So as shown in the slide already, East Antarctica overall does not appear to be contributing to sea level. But it's interesting because if you look at some of the individual methods, so this is kind of breaking down the assessments of mass change. We've got the Antarctic Ice Sheet as a whole on the left, the West Antarctic Ice Sheet, the East Antarctic Ice Sheet, and the Antarctic Peninsula. And what you can see is that for East Antarctic Ice Sheets, which is not here, you can't see my arrow, but for the East Antarctic Ice Sheet, there's actually more disagreement. In fact, the input and output method in blue very clearly gives a picture of mass loss. So it's not surprising that we get slightly different estimates here, because each of these different methods are strengths and weaknesses in terms of what it's measuring on coastal regions where the mass loss is there, others in land, they're sensitive to different elements of the overall mass balance. So it's not surprising that they disagree. You can see in this particular case that the kind of the mean of them gives you a kind of slightly positive mass gain. But I think it's really interesting to know that one suggests growth, one suggests nearly balance, one suggests balance of mass loss. Of course, the other way of looking at this is that, it could actually be starting to lose mass, and some methods are picking that up, and others not quite yet. This is an animation of what the spatial mass loss looks like in Antarctica. Again, it's just really useful to see which parts of the East Antarctic Ice Sheet are losing mass in relation to those marine basins. You can see that really hot spot emerge in West Antarctica, which we've known about for a couple of decades now. But you can see the two marine basins, the Aurora Subglacial Basin, the Wilkes Subglacial Basin, we're both starting to see mass loss emerge from this particular satellite record. Now, interestingly, there are other parts of Antarctica that are gaining more snowfall, and actually, particularly in Durham and Moorland, up here, we are seeing in a warming climate that's consistent with warming, we're seeing more snowfall, particularly in this part of East Antarctica. And at the moment, it may be that those two things are counteracting, which is why we don't see overall mass loss in East Antarctica. But we are particularly worried about this area here. This glacier here, Tottenham Glacier in particular, and the Battlefield as well, around the border, which are thinning, they're retreating, and their catchments hit strongly out of balance. Now, one of the interesting things is that the plots are go through it quite slowly. But one of the interesting things is where that mass loss is occurring, and this is a slightly different study, with the red areas on the ice sheet showing you the mass change, with the red areas showing you negative mass change. And this kind of like band around Antarctica is also showing you the different water properties that are on the continental shelf. And most of Antarctica is a dense shelf or fresh shelf regime, cooler waters. But this little sector here is being characterized as a warm shelf regime. And of course, that sector is exactly where we're seeing the mass loss. So there's a connection here. The other area of warm shelf regime is over in West Antarctica, where we see mass loss emerge quite strongly. There seems to be a really strong connection here between this mass loss in rocks that are being connected to warm waters on the shelf. Okay? And so this is really important. We're seeing on this plot here, we're seeing the basal melt rates of some of the big ice shelves like Tottenham, Moscow University, exceeding tens of meters per year on that ice tongue, because those warm waters are getting under the ice shelf cavities and they're melting the ice sheet from the other side. And again, very recently, there's been some work done looking at observations of water kind of intermediate depth and on the shelf And this section, this is Wilkes Land again, so it's been flipped on its side. And we're starting to see all these red colours here are showing a little change, a warming compared to the last few decades. So this is 2010s minus pre-1990 temperatures. So we're seeing more and more warm temperatures get up onto the shelf in front of some of these glaciers. And these are exactly the glaciers where we're seeing thinning retreat and mass loss. And it's quite interesting that when you plot retreat rates, so we did this in a paper recently where we looked at the paleo retreat rates when deglaciation is actually very rapid, when sea level sometimes rose like several meters per century. And you can see that some of the present day glaciers like Totten, Denver, and Mammoth in particular are actually on a par, sometimes exceeding rates that we sort of say during deglaciation. So this is really, really worrying. These kind of early warning signs that we'd be looking for. And the beauty of hearing someone else's talk is you can actually still stop in one of your own slides now and again. So I've done that here. This is from Wilkes Land. This is in abandoned glacier. You can see the glacier there, the white colours on the left. And what you're seeing in front of me is the ocean floor. And there was a research cruise went in there, and that deep blue is froth on the continental shelf, which we think is carrying those warm waters right to the glacier front. It's eroding the glacier. And this glacier now, not only does it have the highest recorded water temperatures in East Antarctica in front of it, but actually it's now the third fastest grounding line retreats anywhere in Antarctica. It's actually comparable to Thwaites Glacier. And I find it remarkable that there's only one other paper written on this glacier. And there's numerous glaciers like this in East Antarctica where nobody's actually really got detailed observations of what's going on. But when you go and look at places like Wilkes Land, you start to see things happening that are very similar to which you see in West Antarctica. So this is the grounding line retreat. This is the ice surface. This is the point at which the Africans float. And you see it retreating back, as I say, almost kind of 10 years, just a couple of decades. And this is exactly the kind of thing that we're observing in West Antarctica. I mentioned the ocean, and I've just got a few slides to finish on the ocean. Again, some really interesting work that's been done on some ocean dynamics in the last year, which has shown that the meltwater from the ice sheet, the freshwater from the ice sheet, is melting the ice shelves, sometimes from the surface of the bottom, that's much less common, is actually starting to impact on ocean circulation, particularly Antarctic bottom water. So there's a really nice study published recently in Nature showing that this appears to be slowing down and contracting. And what that does is that's bad news because this actually feeds the whole global ocean circulation and could actually be related to things like slowing down of the ABOC in the North Atlantic. But the more immediate problem for East Antarctic ice sheet is that if you weaken that, it opens up a pathway that allows more certain bulk deep water onto the shelf. So this is something, again, it's a warning sign from the oceans that is showing that the East Antarctic ice sheet and its response is likely to have a global impact, maybe beyond just sea level rise. You know, it affects ocean heat uptake and how that's distributed to the oceans, nutrients, etc. And connected to this is also Antarctic sea ice. And this has been fully, well documented in the press over the last year. But Antarctic sea ice has kind of fallen off a cliff in the last year or so. It's not been expected. We knew that it started to decline over the last few years, but 2023 has been remarkable, where it's both its minimum state and its maximum state were the lowest it's ever been. And there will be some other effects here. I think, one of the things that we've learned about here in the ICCI Cryosphere Pavilion is that there is an interconnectedness between the oceans, between the sea ice. And this will have really important impact on ecosystems, on global climate, on population, etc. Another really nice paper came out recently looking at this is the record of Antarctic monthly sea ice extent. So it's been kind of slowly increasing, maybe up to around 2016, and then it was 2017, 16, 17, where it really fell, and then you can see there's a kind of subtle shift here. Possibly in the amount of sea ice that went down here now at the moment. So lots of intra-annual variability, but what people have shown is that this kind of potential shift in 2016 you look at the Southern Ocean temperature anomalies, there seems to have been a warming of the upper oceans as well. So there seems to be potentially a cause and effect here between the sea ice and the ocean heat storage. So that's something. And of course, we also know we've got observations that when you remove sea ice from in front of some of the outlet glaciers, that can also weaken their tunnels and it water, carve more icebergs, and sometimes that response propagates inland. The really unusual thing that happened in the last year or so was a huge temperature anomaly. In fact, I think this is right up there as one of the largest temperature anomalies ever recorded on Earth, when air temperatures are 30 to 40 degrees Celsius warmer than normal across a large part of East Antarctica in March 2022. And this is at least unprecedented in the observational record. And we also know, worryingly, that soon afterwards, or coincident with it, was kind of a breakup of the Congo ice shelf. And I think what Matt's kind of included here in this slide is just this notion that in a warming climate with ocean warming, and potentially with a warmer atmospheric climate that could melt ice sheets from above, these ice shelves surrounding East Antarctica are potentially vulnerable now to breaking up within just a period of a few days. And once you get rid of them, it's like taking the doorstop away, and the outlet glaciers can flow more quickly into the ocean. And there is serious concern that in a warming climate, as the ocean warms, as the atmosphere warms, we might start seeing more of these events. And these smaller, compact, constrained ice shelves, once you get rid of them, then you can easily see a response from the inland ice. So I'm hoping now that might take us quite nicely into the third part of the talk, and we can join Felicity online.
Thanks, Chris. Hopefully you can all hear me.
Yeah, we can.
Excellent. And great. Should be able to see the presentation now. Yeah, so that was a really perfect introduction to what I'm going to be talking to you about today. So I'm Felicity McCormack from Monash University in Melbourne, Australia, and I'm speaking to you today from the unceded lands of the Kulin Nations. And I pay my respects to elders of the Kulin Nations, both past and present. So I just wanted to give you a bit of a broad overview of sea level rise projections to 2100 from multiple sources. And so these plots here from the Intergovernmental Panel on Climate Change 6th Assessment Report, and they show the broad scale projections of sea level rise from thermal expansion. So that's the increase in volume in the oceans as they warm, from glaciers, East Antarctica and West Antarctic ice sheets, and from land water storage. The plot on the left shows the SSP1 2.6 scenario, so that's a heavily mitigated CO2 emission scenario, and the SSP5 8.5 on the right there shows the kind of extreme CO2 emission scenario. So the largest contributor to 2100 sea level rise in both cases is thermal expansion. And then glaciers, Greenland, and Antarctic contributions are the next highest contributors. But their magnitudes really differ depending on the emission scenario. And if we look at the SSP1 2.6 scenario on the left there, we see that Antarctica actually contributes more to global sea level rise by the end of the 21st century than glaciers in Greenland. But if we look at the scenario on the right, so that's the extreme emission scenario, we see that glaciers actually are the primary contributor. Now, one common factor between the two, if you look at the orange line, so that's the Antarctic contribution, you actually see that there's a really huge uncertainty range in the estimates of Antarctica's contribution to sea level rise. So what's going on here? And to kind of piece it apart, it's really helpful to drill down to differentiate the response of the East and the West Antarctic ice sheets. And when we do that, we see a little bit more of the nuance in the story of what might happen in the future. So a key activity that's been going on in the ice sheet modelling community is called the Ice Sheet Model Intercomparison Project 6. And so this is a community initiative that involves over 80 different people, including some of the world's most expert ice sheet modelers, and 13 different ice sheet modelling groups from around the world. And this figure on the top here shows the integrated results from the ISMIP-6 simulations of Antarctica to 2100. So we've got the West Antarctic Ice Sheet in the top left, the East Antarctic Ice Sheet in the middle, and the Antarctic Peninsula on the right, and then the y-axis there shows sea level contributions to 2100. The different coloured bars represent different climate models that are used to force the ice sheet model. So this is really different realizations of atmospheric temperature, snowfall, and ocean temperature that drives melting. And we see that if we look at the West Antarctic ice sheet contribution on the upper left there, we see that West Antarctica is likely to contribute to sea level rise over the coming century, and that's pretty consistent between the different ice sheet models. But if we look at the middle section that shows the East Antarctic ice sheet contribution to sea level rise, what we see is that the East Antarctic contribution to sea level rise is generally negative, and that means that the East Antarctic ice sheet is projected to actually gain mass and hence lower the global mean sea level over the 21st century. And as Chris pointed out, this is really due to the fact that, and as you can see in the bottom schematic there, as atmospheric temperature warms up, the atmosphere is able to hold more water vapor, which means that we have more water vapor available to be precipitated as snowfall over East Antarctica, and that the GRACE images that Chris showed of mass change over Antarctica, where we had red in regions dominated by ocean melt and then blue in regions that are actually gaining mass, it's likely that we might see similar patterns to that over the coming century. But, you know, the error bars here are also really large, and that means that there's, again, a broad range of results, and that might be due to differences in the ice sheet models themselves and the processes that they're incorporating, and also due to different climate forcings. Now, I just wanted to point out that beyond 2100, as the atmosphere continues to warm, we're not going to continue to see increased snowfall. There will come a point when actually we might start to see the atmospheric temperatures are sufficiently high that we would get rainfall as well, especially in the coastal regions of Antarctica, and increased melt of the ice surface. And that eventually, our models predict that the East Antarctic ice sheet will start to lose mass. So snowfall, as I just mentioned, doesn't keep increasing exponentially, and we're likely to see increased ice surface melt. And we see this in projections under extreme warming as well. So these figures here are from a recent paper which breaks down the contributions of different sectors of Antarctica to surface melt and runoff. And while, as Chris pointed out, while East Antarctica and West Antarctica now are predominantly losing mass due to ocean-driven ice melt, under extreme scenarios of warming, which I define as 4 degrees global mean atmospheric temperature or warmer, we see Antarctica actually transition more to a kind of a Greenland-like climate where there's atmosphere-driven ice surface melt becoming a more important process. So if we look at the different sectors here, one thing that's really interesting to point out is that while Antarctica has a kind of a slow increase in surface runoff through kind of 2050, 2060, and then a more rapid increase as the atmospheric temperatures reach kind of 4 degrees. The East Antarctic surface runoff pattern is a lot more linear through the whole 21st century, and we actually see that there's much more surface runoff, or the surface runoff as a percent increases much more quickly in East Antarctica than it does in West Antarctica, irrespective of the climate model scenario. And I think one thing it's important to keep in mind here as well is that polar amplification is a factor here. So while the global mean atmospheric temperature might be 4 degrees, it's going to likely be a lot higher in the polar regions and maybe multiple degrees warmer in Antarctica. Okay, so why do we care about surface melt? Well, there are two main reasons. Number one is that increases in surface runoff directly increase sea level rise, and that's the primary process that's driving sea level rise from Greenland ice sheet. But the other reason that we care is a process that Chris mentioned with the breakup of the Conga ice shelf from the East Antarctic ice sheet last year following the extreme event in March. And this is due to the fact that surface runoff can actually weaken the stability of ice shelves through forming large fractures in the ice, which can increase the vulnerability of these ice shelves to calving and collapse. And we saw such a process occur in the Antarctic Peninsula in the Larsen B ice shelf in 2002. We have tended to see that happen more in the Antarctic Peninsula, where atmospheric temperatures are warmer. But it's possible that, and as the previous slide showed, if surface melts in East Antarctica becomes much more dominant, then East Antarctic ice shelves could be more vulnerable to similar processes. Now, ice shelves actually provide a really important stabilizing effect for the upstream ice. So when they collapse, we see more ice being transported to the grounded ice sheet into the ocean, and that leads also to increased sea level rise. Okay, I showed earlier that the Intergovernmental Panel on Climate Change 6th assessment report predicted that Antarctica would lose up to kind of 30-ish centimetres of sea level rise to the end of the century. But the report actually couldn't rule out multiple metres of sea level rise to 2100 and up to 5 metres of sea level rise to 2150. These uncertainties are largely due to processes of rapid ice loss from Antarctica being imperfectly known, and you know, there's a lot that we can glean from the paleo record to help us there, but you know, some of these processes will require much more detailed monitoring and observational work in Antarctica and in regions of East Antarctica, as Chris pointed out as well, that are typically a lot more difficult to access. So I wanted to talk a little bit about what could happen to Antarctica or in East Antarctica on longer timescales, what happens beyond 2100. And unlike in West Antarctica, it's unlikely that we've exceeded a tipping point in East Antarctica. So what do I mean by a tipping point? Well, it's this notion that if you force a system beyond some critical threshold, then even if you remove the forcing, that change would perpetuate and would be irreversible. And so in West Antarctica, there's some early evidence that where we have exceeded a tipping point already, and that some parts of West Antarctica would deglaciate irrespective of our climate emissions scenario. We're not facing that same scenario in East Antarctica yet. However, for 4+ degrees of warming, large parts of East Antarctica could retreat irreversibly. And these figures here are from ice sheet model simulation that looked at how the Antarctic ice sheet responds to slowly increasing temperatures. And what you see is that West Antarctica deglaciates kind of early on for relatively low atmospheric temperatures, although, you know, I don't think we can actually argue that the impacts of 1 and 2 degrees is negligible. We've already seen extremes in climate change across the world, and, you know, I think there's strong impetus to ensure that we're keeping our atmospheric temperatures at an absolute minimum, atmospheric increases in temperature. But yeah, so we see that for 1 to 2 degrees of warming, large parts of West Antarctica could deglaciate, but it's not until we get to kind of 4-ish degrees Celsius that we start to see those subglacial basins that Chris pointed out start to deglaciate. The bottom panels also show what happens when we decrease the temperatures really, really slowly in these ice sheet modeling simulations back to pre-industrial temperatures. And what is really clear here is that even when you decrease temperatures back to what they are in present day or lower, the East Antarctic ice sheet takes much, much longer to grow back. And some parts of East Antarctica don't fully regrow to present day configuration, even if the temperatures are reversed to the present day levels. And so I think one thing that this highlights, as I've indicated on the slide there, is that if the Paris Agreement is not met, then East Antarctica, or Antarctica and East Antarctica's long-term sea level contribution will dramatically increase and exceed that of all other sources. Now, these simulations that I've shown you have really been conducted with standalone ice sheet model simulations. That is the ice sheet models that are not coupled to the broader climate system. But of course, the ice sheet doesn't stand alone. There are incredibly important feedbacks that operate between the ice sheet, the climate, and the solid earth systems, as you can see in this schematic here. There are a number of modelling, international modelling groups that have made really exceptional progress towards coupling ice sheets into general circulation models to ensure that we're capturing feedbacks between the ice sheet system, the climate system, and solid earth, but we're still not quite there yet at a broad level. So there's a lot of uncertainty associated with the impacts of mass loss on different systems. And there are a couple of different studies that are starting to show that what happens in one system can actually amplify or dampen changes in another system. And when it comes to climate tipping points, which I mentioned on an earlier slide, we call these system-to-system amplifications tipping cascades. So to illustrate the point, this is a figure from a recent paper that shows that as the Greenland ice sheet melts and global sea levels rise, that actually amplifies and accelerates ice melt from the Antarctic ice sheet, which then again accelerates ice melt from the Greenland ice sheet. So even though we have improving projections of what's happening in East Antarctica, where our models are able to capture the important processes increasingly well, we're improving other capabilities of our models. There's still a long way to go in terms of capturing the feedbacks between different systems and different climate tipping elements. And there's potential that we're not going to anticipate really important changes simply because we don't have enough of a complete state of knowledge of the whole system. And Chris highlighted that in the case of the extreme sea ice decline that we've seen in recent years in Antarctica, where we just weren't able to predict such a marked decline in the time frame that it happened. And this highlights the fact that it's absolutely essential to limit warming as much as possible now. Okay, so I talked a little bit about sea level rise impacts and the fact that we have this uncertainty associated with where global mean sea level could be in 2100 and 2150, and that large uncertainties remain in some of the understandings of ice sheet processes alone, but then the feedbacks between those different systems. And then just building on what Chris mentioned earlier, it's not just sea level rise that we care about when it comes to East Antarctic ice sheet mass loss, but ice mass loss from Antarctica has huge implications for the climate and the ecosystem. So Chris mentioned the global overturning circulation, particularly the formation of Antarctic bottom water, which is really, really crucial in driving that ocean circulation that essentially regulates heat transport around the globe. Freshwater fluxes have also been shown already in the Antarctic Peninsula to significantly impact krill populations, which are highly vulnerable to mass kill events as the ocean freshens. And then, of course, as we see more freshwater inputs to the ocean surrounding Antarctica, we'll see impacts to sea ice, and that can have impacts to the ecosystems that rely on sea ice formation and production. So I guess I'll leave it there, but wanted to finish up by saying there are a lot of uncertainties in understanding how East Antarctica will respond to climate change, and they're inherent both in ice sheet processes, but also in interactions between the different systems. I showed you some projections that showed that under a small amount of warming, we could see increased surface melt in East Antarctic ice shelves, leading to significant changes. But once we start to, or if we were to go beyond that to more extreme increases in temperature, we could see irreversible retreat in East Antarctica, leading to tens of meters of sea level rise, as Chris highlighted, is likely to have occurred during warmer periods in the past. And I think it's just incredibly essential that that we improve our understanding, not just of the magnitude of the change, but the timescales over which that occur. And to be able to do that, we really need international and committed funding into sustained monitoring, observing and modelling. And I'll leave it there and hand back over to Chris.
Fantastic, thanks, Christine. So I just had a final slide really, just to summarise, just to mention the ecosystem impacts. So we actually have a new funded project to look at how changes in sea ice. And last year, tongs halving, or increasingly halving in the future, would impact on most penguins. But the key conclusions I get from this talk are that we know that the East Antarctic ice sheets responded to past warm periods that were similar, were only slightly warmer than present. Likely contributed several years to sea level rise, and there's a clear warning from the past. Current observations show emerging signs of mass loss. So if the East Antarctic ice sheet were starting to respond in the next few decades, the observations we're seeing in Wilkes-Barre, for example, will be consistent with that, driven by warm ocean currents. At the moment, they seem to be compensated for by increased snowfall. But as Felicity mentioned, that won't last forever. And if that starts turning to rain or if the mass loss increases, we will quickly tip the system into one which is losing mass. So the East Antarctic ice sheet, I think, has potential to generate several years of sea level rise if 1.5 is exceeded. And with 2 degrees and beyond, it's likely to awaken this sleeping giant, and that's when we're talking double digits of sea level rise potentially. And that melting has increasingly far-reaching impacts. It's not just about the impact on sea level, but the impact on the global ocean circulation, climate systems, sea ice production extent, and of course, these delicate polar ecosystems. So thanks for your attention, and I'll finish there.
All right, thank you for all the speakers, and thank you, Chris, for taking over Matt's slides. Those are so clear and spelling just like your slides. Do we have any questions from the audience? Robbie.
So you said when you remove the floating ice shelves, that's like taking out doors. What's the physical reason that when you remove an ice shelf, the ice on the land slides into the sea faster?
Yeah, so that's a really good question, because not all ice shelves are equal, in the sense that if the ice shelf is kind of constrained and it's kind of clinging onto land either side of it, that's when it's quite strong, and we know it exerts what's called a buttressing force on inland ice. And we can actually, there's been a really nice work that's been done last few years where they've actually looked at each individual ice shelf and they've worked out what proportion of the ice shelf is exerting a buttressing force. So if you were to remove that part of the ice shelf, you would expect to see a response from the ice sheet flowing more quickly into the sea at the moment. There are other ice shelves that are unconstrained, that essentially just float out into the open ocean and spread apart, and they're called passive ice shelves. And if you were to remove them, there'd be very minimal impacts on the inland ice velocity. So I think there's an interesting lesson here that actually you've got to understand the nature of each ice shelf to know what the impact is likely to be once it's removed. And so we've seen, for example, we did a study in Wilkes-Barre a few years ago where there was a huge breakout of land-class sea ice that had been there for, as far as we know, quite a few decades. It's always still been ice in this bay. And there was a breakout of it in 2007. And immediately after that, the ice tongs all collapsed. And there was a velocity increase, etc. So that's because they were in an abatement that was exerting. So you have to look at each individual ice shelf with the extent to which it's constrained.
I've got a question. Sea level rise 2100 is going to be another generation's problem. But what keeps sort of bugging me about loss of life, both in Greenland and Antarctica's effect on both ocean currents and ocean temperature and weather systems and climate systems that could have a big impact on infrastructure now. And infrastructure, I'm thinking more agricultural and also river transport. What we're seeing on the Amazon right now, the Mississippi River, especially the last year. This might not be in your bailiwick, but is anyone doing a lot of heavy lifting work on that, or is it just the systems are too complex for what we're really going to go on?
You mean the impacts on weather systems, or
on weather systems, whether it be seasonal monsoons, and jet stream, and just all that.
Yeah, so obviously, I think I'm glaciologist, I'm interested in the ice dynamics and the impact on sea level. We do know that climate change is leading to more and more extremes. If you look at the IPCC report, they've got some brilliant chapters now that specific to regional climate change, how you might expect more to, how you might expect to see droughts that's more intense in Northwest Europe, how you might expect to see a weakening of the polar vortex, which will sometimes push huge amounts of cold air into North America, and heat waves can come along. So there's going to be we're just ramping up with the energy in the system really towards more instability and towards more extremes. I mean, that's how I would answer that question. There may be other people in the room actually, but that's why I just want to do it. But that's how I read it.
Is there anyone more qualified?
Well, I work from the office. I'm primarily an oceanographer. Although I do work from the office. I mean, I think there have periodically been studies looking at fresh water in the ocean, but typically focusing on the ocean circulation part. It's a valid kind of knowledge gap,
Right.
In terms of what the effects might be. We understand much better like thermal coupling of things. The atmosphere tends to care more about the thermal coupling, so I suspect the response might be indirect. So the ocean circulation cares about pressure throughput, and then if the ocean circulation changes, you start to mess that with heat transport, then that's when I think you'll see the more. And think about sea ice, of course. The distribution sea ice is hugely important. Air sea exchanges. But I wouldn't want to say with any definitive. I think there will be check effects, but I don't think we understand what they will be.
Yeah.
I have another question. Bill's waiting. So this like rapid ice cliff collapse scenario where we could really see a high level of sea level rise really quickly. There's obviously debate about whether that's real, whether that's going to happen. Do you think we'll get to a point, if it hasn't happened, where we'll be able to say, okay, no, this is not a thing? Do you think if it gets to like 2070,
And you say,
and we'll say, we don't see it yet, so it's not a physically realizable thing, or do you think it's always going to be there?
I think so. I thought I had a slide that kind of, I do have a slide. I thought I had the actually IPCC slide, sea level rise slide, but I don't. But you're talking about this, what's known as marine ice cliff instability, and this is the kind of rapid removal for those who aren't familiar, where we don't. So the other instability is the marine ice sheet instability, which is theoretically very robust, unless you're really gripping the ice from sides. We know that if you have a reverse sloping bed, the ice goes into a kind of runaway collapse until it reaches that higher ground. Now, the marine ice cliff instability doesn't require a reverse sloping bed. It can be on a flat bed, it could be retrograde, it could be sloping land. But the key thing here is that you take away the ice shelf, like some of the methods we've just discussed, and then you essentially expose cliffs at the grounding line, the point where it begins to flow, which is effectively like rock falls, like a steep cliff that starts to collapse into the ocean. And of course, as you do that, you then expose it steeper and steeper because your cliff gets bigger as you go back in load. And it's interesting because there's obviously a little bit of controversy around this. My understanding is that this mechanism was put into some of the models because they couldn't get East Antarctica in particular to respond during the past war period. So we knew global sea level had to be much higher. We know that the ice sheets had to be greatly reduced during those war periods, but when you ran the models, they didn't reglaciate enough. So we were missing some processes potentially. And so this was also based on observations of collapse in places, and you can actually go to present day, you can observe cliff collapse taking place, carbon fronted glaciers. And so, this was put into the models to help reconcile the observations to sea level with what the ice sheets were doing. So, I would say it's not underway yet. There's no evidence it's underway, but it's possible in a warming atmosphere or ocean. And we know, as you just mentioned, that if it does happen, this is what could lead to really, really, really high rates of sea level rise. I'm aware of a number of groups working on this around the world at the moment, where they're actually going to ice cliffs. They're measuring the water depth, they're measuring the cliff heights. They can use some of the theory that's built into these models to say, well, actually, we would expect this much calming to be taking place if instability had started. There's no evidence that it has started anyway yet, but I think we will be able to say at some point, yes, it does, or no, it doesn't. And actually, I'm reminded, with colleagues next to me here, that the actual GIA effect, that the land rebounding as the ice decreases, could also be a way of shallowing the water, dampening down some of these instability, whether it's the green ice sheet instability or green ice instability. That will take place a slightly longer time scale, might be sufficient with a rapidly legislation. So that's a very long-winded answer. I've been taken to act. I don't know if Felicity wants to come in, because obviously she's a modeler and I was aware of this conversation.
Do you mind repeating the
Sorry.
question?
Yeah, I'm having a little bit of trouble hearing, sorry, so.
Okay.
Well, my question is, do you think we'll get to the point where we'll know if marine ice cliff instability exists or not, just from whether it's
Sorry, I caught whether or not we know if the marine ice sheet instability exists.
yeah.
Sorry, would someone mind typing the question into the chat, please, just so I make sure I understand? Sorry, the audio's cutting out a bit.
So it's okay for this. Yeah, I can deal with it.
Sorry.
Yeah. And it's this is those kind of abilities kicking in, particularly very nice things because you end up on that dash line. I do think it's worth noting actually that if you look at a similar plot for Greenland mass loss is now tracking slightly above the worst case scenario, the 8.5 scenario for this decade. So it's a point that we're making these environments that every time we get new observations and new weather studies, it tends to be worse. You know, you're asking about, will we know if it hasn't happened, which will be good news. But there's very little good news with F-slashes.
That relates to the question I was going to ask about early warning systems. So we saw that schematic, and what it tells us is that there's a sequence of observable events after, we have to fill that sequence of observable events to follow that trajectory. Yeah. And so I think, I'd love to talk to you at any longer time. We're not going to we're probably going to exhaust this topic. So but it'd be really good to just get your thoughts on, what you think some of those early warning signs might be. You mentioned the certain kind of deep water in certain areas of the and I guess some of the stuff I've absorbed and will be involved here at COP28 is around observations to support the science. And so just any thoughts you've got on I think what those early warning
somebody who works on the observations, particularly on ice sheets. The three kind of links, it's like taking a health check with somebody, the three things you want to go and check, I would say, is the ice surface thinning? Yeah, so and we've got satellites that can give us that data on a weekly time scale, but is the ice surface thinning? Is the grounding line retreating? So the ice surface thinning is something we can, with a few corrections, we can get quite easily. Is the ice velocity? That will be another kind of warning sign. If you're looking at a particular glacier, you saw it thinning and the velocity increasing. And again, that's something you can get ice velocity in Antarctica in 6 days. And then is the grounding line retreating? That's the really critical thing. Now, that is a bit more difficult to map, right? So we tend to overget that annual time scales. But to me, if you're going to decide, and I have thought about this and thought about building these research proposals. The amount of satellite observations we've got now with machine learning, it should be within our grasp to set up a kind of system that pulls down these data and will flag to you in a certain catchment when those three things maybe are happening. And then where I think we really need observations, going back to your first point, is in the ocean. That's a kind of a little bit of a black hole at the moment. We have very little ocean observations. And so we don't always know whether there's warm water on the shelf. We don't know whether it can get close to the glaciers and do the damage. And we don't know what the long-term trend is in the ocean warming either, and what the decadal sort of frequency variability might be. So on the one hand, I think the glaciological observations could easily give us an early warning sign. But of course, what we really want to do to help projections is kind of model what's going to happen to the oceans, how they will attack the ice sheet over the next few decades and centuries. I think those ocean models are ocean observations where there's a really need more data.
I'm actually got to go to something else now. But I just wanted to say this was a great presentation on the three of you. It's a shame that I wasn't here, but I thought you guys did a fantastic job. So
Thank you.
I'll
be around most of the week.
Okay,
So some combination you'll be able to find us.
Listen,
If we see you again,
I can't find you, and if I don't, I'll definitely contact you, think about the early warning system.
Yeah,
That's
yeah.
relevant to our role in this.
Yeah.
We'd like to develop stuff,
yeah,
it'd be good to.
that sounds great. Yeah.
All right, thanks guys, thanks everyone, really glad I found out about this section. Very good. Yeah.
Bye.
Uh,